Thank you very much. Welcome to the second plenary session. I know that we've had a number of new registrants that came in yesterday, so I want to welcome you on behalf of the New York Catalysis Society and from City College. Welcome to New York. This is the city that doesn't sleep. And so I encourage you, while you're here at any time of the day, to explore New York City. If you go to the east, you'll see some money. If you go to the west, you'll see Broadway and Times Square. If you go to the north, you've got Central Park. And if you go to the south, you'll see everything else. So have a great time in New York, but before you go, we have a special session that you should attend first, which is this one and a few others. While you're exploring, be sure to have a bagel, be sure to have a bialy, be sure to have pizza by the slice, have a knish, and then have a hot dog and mustard. And you'll be all set to go back to your homes and remember what a great place this was. And so as you're having those great foods, you can discuss this next presentation for the Emmett Award. Paul Emmett was born in 1900 in Oregon, and he met Linus Pauling in high school. He got his Bachelor of Chemical Engineering at Caltech, Oregon, and then went to Caltech to get his PhD. And there he focused on autocatalysis of metal oxidation reduction. And there, Paul Emmett and Linus Pauling also studied the structure of barium sulfate. And so they had a real connection over the years. In 1944, Paul Emmett came to New York City to work on the Manhattan Project. And then in 1955, went south a little bit to Johns Hopkins University to become a professor of chemistry. Along the way, Paul Emmett, with his colleagues, Stephen Brown and Edward Teller, helped build the foundation of modern catalysis by developing a method of measuring the surface area of materials using condensed gases. Professor Emmett's achievements resulted in the election to the National Academy of Sciences and several honorary doctorates from universities around the world. I would like to bring up today our newest distinguished colleague who is being inducted into the Paul Emmett Award list. I'd like to bring up Professor Alex Bell to introduce this year's winner, Thomas Jaramillo. Professor Bell?
Good morning, everyone. It's a pleasure to be here and to see so many friends and acquaintances and see you all in person. I also enjoyed Marco's introduction to New York. Having grown up in a one-block radius right around here, this is all very familiar territory. All those words you said are very familiar. So indeed, everyone enjoy New York. New York, as they say. So this is a special year because we have not one, but two Emmett awardees. Jaramillo, who I'll introduce in a second, and also Beatriz Roldan Cuenya, who will be speaking tomorrow morning at the same time. So Tom is a native of Puerto Rico, grew up in San Juan, and after finishing high school, came out west to California, did his undergraduate work at Stanford, and then went south to Santa Barbara to do his doctoral work with Eric McFarland. That's where he first became acquainted with catalysis. And then he received the Hans Christian Ørsted postdoctoral fellowship, which he took with him to go to Denmark and studied with Pete Korkendorf at the Technical University of Denmark and in the Department of Physics. And after that trajectory, he came back to California, and in 2007, and ever since, he's been a member of the Chemical Engineering Department at Stanford, where he's now associate professor, and he's also the director of the SunCat Research Center that looks at many, many different aspects of catalysis and involves 70 researchers. Tom's research is all about understanding catalysis at the fundamental level, synthesis of novel types of materials, characterization, and their investigation for many different types of reactions. But in recent years, it's focused on electrochemical processes for producing hydrogen, reducing nitrogen to ammonia and other compounds, and also CO2 reduction. He's authored over 200 papers. They're all very highly cited, 45,000 and more citations. And for this, he's received a number of awards, which I will not list, but named lectureships. He today is the head of a group of 25 young people, postdocs and graduate students, and more than 10 of his former group members are now in academia. So this is quite a tribute to Tom's accomplishments. I also want to say that Tom has used his Latin American heritage and been a model for people of Latin American extraction and helped to guide them and develop their careers, and he serves as a role model. So I think without further ado, we should give a round of applause for Tom Jaramillo, who will give us Emmett Award. Tom?
Good morning, everyone. It is outstanding to be with you here today, here in New York, in person. It's been a long time, my first big conference. I couldn't ask for a better one to share with you. Just talk shop, Catalysis. It's amazing. It's been a wonderful couple days already. Looking forward to the week ahead. I want to say thank you to the Society. Thank you, Alex, for a wonderful introduction. Thank you, Marco, for kicking us off this morning. Thank you to all the organizers for making this happen under the most challenging of circumstances. It's really my honor to be here today, a privilege for this opportunity to share with you thoughts on catalysis, really for what could be a future ahead in terms of the fuels and chemicals industry, and developing catalysts and chemical processes to get us where we need to be, which is to live and thrive with our community, humans, environment, in perpetuity. So before I dive into some of that, I just want to say a few words about Paul Emmett from my perspective. You heard a little bit about his background. He was a very, of course, accomplished scholar, worked in many different areas, published over 160 articles in his day, which I think by today's standard is like 1,600 articles at a time where all data was collected with analog instrumentation instead of digital. Nothing was electronic. There was no PowerPoint, there was no Word, no electronic submission of manuscripts. Everything had to be mailed in. There wasn't even Federal Express to send it in quickly. So really impressive what he was able to accomplish. And I wanted to point out some of the areas that he touched on in his research career. Formation of water from hydrogen and oxygen on nickel catalysts. That was his dissertation work at Caltech. Nitrogen fixation to ammonia. BET theory, of course, and catalyst-specific surface area measurements. Fuel production by Fischer-Tropsch. And uranium separations. And there's enough we can talk at length about his contributions in these areas. I think first and foremost, nowadays, he didn't have the luxury of this, but we all do have access to the electronic versions of articles on these cases. I do encourage you to go take a look. They're readily findable, archived electronically. Very elegant work. And the themes, interestingly, are going to touch on many of the themes that we'll be talking about today in this morning's lecture. So we'll be talking about, for instance, how we can convert water into hydrogen and oxygen. We'll be talking about nitrogen to ammonia. We'll be talking about converting carbon dioxide into fuels and chemicals. A big distinction between some of the things that Paul Emmett worked on versus things I'll be talking about is he was focusing on temperature and pressure-driven catalysis. I'll be talking about the electrification of these processes, how we develop electrocatalysts. But I'm also going to provide a framework for unifying concepts of electrocatalysis and thermocatalysis. We'll get to that in a bit. Everything I talk about today will be founded upon a very important point, and that is that we do have to normalize the number of active sites, normalize the surface area that is foundational in our field, building off some of the things he had done. And he did make lots of contributions to the Manhattan Project vis-a-vis uranium separation, uranium enrichment. And to those of you who are fans of uranium chemistry, I will not be focusing on uranium chemistry today. We'll focus on some other topics. I also want to thank W.R. Grace for sponsoring his faculty appointment, his professorship at Johns Hopkins University, and for half a century of sponsoring this award, the Emmett Award. Here's to the next half century ahead. All right, 3 key points, they're foundational points that I'm going to be touching on throughout the talk. I'd like just to have this in the back of your mind. Number one, that there is an opportunity to innovate in the fuels and chemicals industry for improved sustainability. Lots of opportunity to do that, and we need to do that. I want to make another point that competition work in concert with experimental work is essential to innovation ahead. We'll see lots of that as a theme throughout the talk. And that fundamental science and engineering is absolutely needed if we want to innovate for the future. And it's really important to work on model systems, work on applied systems, and to bridge these systems. So that's another theme that we'll be hearing about today. Now, what I'd like to start is with one of the most impressive achievements, perhaps the most significant achievement in human history. And that is our ability to produce fuels and chemicals at scale and get them to the billions of people on Earth and at extremely low prices. You can imagine how cost effective 50 cents a kilo, $1 a kilo, $2 a kilo, what can you go to the grocery store to buy for those prices? You can buy hydrogen, ammonia, gasoline, plastics, right? Thanks to really innovation in science and engineering that has figured out how to take resources that Mother Nature has given us and convert them into molecules of use. These are just some of the 7,000 different molecular products that we produce every single day, sent around the globe, and you can see the scales, tens of megatons, hundreds of megatons, a gigaton of molecules. These are molecules that we need to live. And so the question is, why would we want to do something different? They work so well. There's a lot of reasons why. Number one, they're not intrinsically sustainable processes, that's a challenge. And number two, while they do access billions of people, there are also billions of people on Earth who are not as well connected into to this system as we are here in the world. So there's lots of motivation to innovate ahead. Now I get to work on those projects with a tremendous team of scholars from the SunCat Center. We're a partnership between SLAC National Lab and Stanford University. You can see some of the senior leaders of the SunCat group. We have theoreticians, we have experimentalists, we have people looking at catalysis in different ways and shapes and flavors. The idea is how can we design and develop catalysts for the future, for sustainability, for energy. So it's well rooted in theory, really physics-based modeling, understand how catalysts work, how reactions work. We use that as input to design and develop catalyst systems that we synthesize and characterize using advanced tools both at the university as well as the national lab, including a synchrotron and a free electron laser, among other tools. We of course evaluate and figure out what works and what doesn't, feed it right back into the theory, and wrap it all with a cozy blanket of data science, trying to extract more meaning out of that data than without. Now, if you want to reinvent the future, you need some drivers, some forces at play that are going to shape that future. And one of the key drivers in our community is the dropping prices of renewable electricity. Really amazing, astounding what's happened in the last decade, where we're looking at the levelized cost of electricity for unsubsidized wind, unsubsidized solar, and now we're down to 4 cents a kilowatt hour on average. Some sites are down to 2 cents a kilowatt hour, even 1 cent a kilowatt hour, and we're on a tremendous glide path of dropping price of renewable electricity that behooves us to make use of it. So that's really a major factor for thinking about how we can catalyze reactions using electricity as an input. But don't think that this is a new idea. These are large large-scale industrial processes that have existed for many decades. I specifically am choosing photos that have come back from decades past just to show you how long we've been doing this as a science and engineering community. Next time you pick up a can of soda, that aluminum that you're touching came from an ore from underground that was mined and then reduced electrochemically to put it into its metallic state. Please recycle that can of aluminum, by the way, and it takes 5% of the energy to get it back from recycling than it does to get from the ore to begin with. Next time you pick up a credit card, it's probably made of polyvinyl chloride, PVC. And where do we get that chlorine from? From the chloralkali process, it produces base and chlorine. Also, at very large scales, that's an electrified process. And of course, those water electrolysis has been around for about a century at the commercial scale and right for reinvention. So this is really to show that this is not pie in the sky ideas. The question is, how can we develop catalysts? How can we develop processes that can make these products at scale inexpensively using inexpensive renewable electricity? So if we want to create that new paradigm, I'm going to present 4 numbers. These are very aggressive cost targets. But this is how we can kind of flip the script. So the production cost of any chemical, dollars per kilo, is going to be, of course, a function of its capex and its opex. And so we need both of these terms to be inexpensive. We need renewable electricity to be inexpensive. We need carbon capture to be inexpensive if we want to make a carbon-based product. We need energy storage to be cheap. And we need an electrolyzer that can take these inputs, do the chemical transformations that we're interested in, and make the products that we desire. So what I'll be talking about today is what is largely in this bucket here of how can we develop electrolyzers with inexpensive catalysts that can do the chemical transformations that we desire. And that really brings us to a view of what the future should be. We need fuels for transportation, we need chemicals, we need building blocks, we need fertilizers, we need lots of types of molecules. We typically get them from fossil resources. We need to continue doing that because that's how we're going to provide for billions across the globe. But how can we build a complementary technology that one day will be the majority technology decades ahead that can make all of this in a sustainable manner? And we need catalysts to do that. All right, so I'm going to go into 3 examples of how we go about these chemical transformations, how we think about them. First, with a focus on hydrogen, then a focus on carbon-based products, and then a focus on ammonia. Let me take a sip of water if I may, and we'll continue forward in just a second. All right, so let's dive into hydrogen. So hydrogen we already talked about, very important molecule made of 70 megatons a year. We use it for oil refining, we use it for ammonia synthesis, among others. The question is, could it be an energy carrier? Can we increase its production rate by saying 1/4 of the magnitude to hundreds of megatons a year and use this as a clean energy carrier? Now, the hydrogen that we normally get, of course, is from fossil fuels, predominantly from steam methane reforming, which produces a stoichiometric amount of CO2. So the question is, how can we make this hydrogen without the CO2 emissions? And there are many ways to do this, in fact, but one way I want to talk about today is through water electrolysis. So how can we take renewable electricity and feed it into electrolyzers or split it into hydrogen and oxygen? Now, as I mentioned before, it's already a commercial technology, but we need to make it better, we need to make it cheaper. And I'm showing you some really designs for, modern designs for water electrolyzers, one from ThyssenKrupp. Here's a 20 megawatt module that is commercialized today. Here's more of a concept plant, 100 megawatt facility that was designed by Proton Onsite, which is now owned by the Norwegian electrolysis company, formerly Norsk Hydro. And you can see where the costs are really coming from. We need to lower costs on all fronts. There's 1,000 levers here. There's not a single lever that is so significant that if we just improve costs on that one lever, we can make it cheaply enough. So we need to work on all of these areas. Lots of fundamental R&D to hit the DOE targets. What are the DOE targets? So Secretary Granholm and DOE recently announced Earth shots, several Earth shots, one of them on hydrogen. And the goal is to get hydrogen down to $1 for 1 kilo within 1 decade. Very ambitious cost targets. So we're off by a factor of 4 or 5 today based on modern technology. And again, there's lots of areas of need to be able to lower these costs. So what are some of the areas of need? We need lower cost catalysts. We need to reduce or eliminate precious metals. These systems that we're looking at here are loaded with platinum and iridium. We need lower CapEx for water purification. A lot of the cost of this plant is really the water management. You're taking in a feedstock, even if it's tap water, it needs to be highly purified for the commercial grade electrolyzers today to work. Another question is how do we couple these smartly to renewable electricity? So these are 3 themes I want to talk about and some of the technologies we're building in that space. Now, if you want to get rid of precious metal catalysts, it's good to have an idea of where to start to look. And really, a lot of this in my world started by looking at biology. And thanks to Emmett and Jens some years ago, they were doing atomistic models of nitrogenation and hydrogenation. These are Mother Nature's catalysts for hydrogen. They're basically every bit as good as platinum, but no precious metals inside. And so they were really trying to understand what made these things work. And what they found was that there were certain sites in these enzymes with uncoordinated sulfur that seemed to be the active site for the reaction. And the descriptor for this was the delta G of absorption of hydrogen, which was very close to zero. This is the Sabatier principle put into place. And so when I was a postdoc working together with E. Kortendorf at Technical University of Denmark, as Alex has pointed out, that really inspired us to take a look at molybdenum sulfide as a solid-state catalyst that could perhaps resemble some of the features of this motif we see in the enzyme, these undercoordinated sulfurs that decorate the edge of this two-dimensional material. And sure enough, it turned out to be a very active catalyst. So we, through model studies where we did ST imaging of well-defined nanoparticles, we could basically ascribe the catalytic activity to the edges, which is exactly what the theory predicted the catalyst activity to be. And then at Stanford, some early-stage researchers that I got to work with, Chip O, former PhD student, Jacob, former postdoc, started synthesizing all kinds of different formulations of molybdenum sulfides, nanowires, porous materials, small molecular clusters. The long and short of it is the more edge sites you build, the more active your electrode would be. And this is, again, founded on theory, based on biology, based on understanding how non-precious metal systems work. Now, here's the data that shows our measurements on these systems. This is voltage versus current. I'll be showing a lot of voltage versus current curves today. And the way to do this voltage scale versus a reversible hydrogen electrode is that if you hold your electrode at 0 volts versus this on this scale, that means the reaction's at equilibrium. So you're making oxygen or making hydrogen just as fast as you're oxidizing it away. As you tilt the voltage more and more negative, you're driving it towards the reduction process or the formation of hydrogen. And you can see for formulations 1 to 2 to 3, as you build in more and more edge sites, you get that current to turn on closer and closer to equilibrium, which is a good thing because it's a more efficient catalyst. Now note that this is still far from zero, 150 millivolts or so. Platinum basically takes off right away. That's how good of a catalyst it is. And to my knowledge, no human being has ever made a non-precious metal catalyst that gets even close to platinum. So platinum still can't. However, now we have some non-precious metal systems that can survive in acid and show some decent activity that might be worth pursuing further. Now, one thing I'll also point out, these are very fundamental measurements of fundamental electrical systems where we're tracking current densities on the order of 10 milliamps per square centimeter. And when I talked to industry partners back at that time, they thought that was nice, but they would tell me, Tom, our stuff runs at 1 amp per square centimeter. So that was the motivation for us to think, how can we take this further? But we needed more catalysts. And so we did, now that we had a good descriptor that we could work and we had some idea of what some new non-precious metal systems might look like, we went about catalyst discovery effort, really engaging computational scientists, Frank Herbert Peterson, Charlie Tsai, among others, exploring a very wide space of transition metal sulfides, and phosphides, and phosphosulfides, all kinds of different formulations. And what we found, I suspect, is not terribly surprising in our world, that in fact this descriptor of delta GH being close to 0 is where you find the best catalyst. If you bind hydrogen too strongly or too weakly, you will end up off the top of that volcano. So with a number of different catalysts in mind, we start to try to turn these things into real electrolyzer systems. And that was the 800-pound gorilla, or the elephant in the room, of how do these catalysts function in real devices now that we have some catalysts to work with from a fundamental perspective. So we started tooling the lab for device fabrication and testing. We don't want to just understand how they work under the most intrinsic and well-defined conditions. We want them to work under real technological conditions. So we developed, we procured a number of different tools to do fabrication of membrane electrode assemblies and testing of these systems. And so here's some of our first results. Former PhD student Desmond started taking some of those formulations of aluminum sulfides, and phosphosulfides, and phosphides, and others. He made them into inks, which are compatible with how modern commercial-grade electrolyzers are made today. It's basically a sheet of Nafion with 2 carbon gas diffusion electrodes on either side. He would put these catalysts on them and run them. So here's your voltage current curve. Now we're operating at 1 amp per square centimeter, which is where industry and industrial systems operate. The iridium platinum system is still the best. They're still the best catalysts that we have that operate under these conditions, generally speaking. But now if we replace the platinum with non-precious metal systems, Number one, you can see that we do get the current densities that we desire. We do have to pay a 0.2 volt penalty though, because again, no unit has ever made a non-precious metal catalyst that works as well as planned. But this at least offers a trade-off possibility. You can have a lower CapEx system that operates less efficiently, or a higher CapEx system that operates more efficiently. If you're paying 10 cents a kilowatt hour on electricity, it's a no-brainer. You go with this system, if you're down to 1 or 2 cents a kilowatt hour, it's not so obvious anymore. And so with this in mind, this is really pointing the direction towards where this technology could possibly go. Pardon me. So we wanted to take this the next step further, and that is to get these into some real commercial grade systems, not just ones that we fabricate in lab, but one that industry creates as well. So here's Mackenzie and Rory. These are some of our catalysts. This is cobalt phosphide on carbon. Again, if you do a polarization curve, it's exactly what you expect. Now we're driving 1.8 amps per square centimeter out of this thing. By the way, this is a real commercial system that is sold by Proton on site. It contains lots of platinum, lots of iridium. 86 square centimeter system, operates at 400 psi, hydrogen pressure 50 degrees C, 1.8 amps per square centimeter. It was not a surprise that we paid that 0.2 volt penalty for everything we talked about before, but the more open question was how long would this thing last? And we ran this experiment for 1,700 hours before it was time for them to flip the switch because the project had ended. It did not die catastrophically. We have no idea how much longer it would last. But to give you a sense, the turnover number here was about 10 to the 5. So it produced 100,000 molecules of hydrogen for every cobalt phosphide unit that was in the system with no end in sight. So this is very promising that these catalysts aren't just fundamentally interesting, but they actually have perhaps some technological relevance. So we continue to push that forward, but there's other questions that we've been aiming to answer, and that is, can we work with impure feedstocks? So everything I showed you is working on very pure water, but as I mentioned, that's a very big capital cost for a hydrogen plant. What if you could work on impure feeds? And so here's some work from Diana Alini, Joe Perryman, Adam Nylander, on developing electrolyzers that could use the most impure of large-scale feedstock that we've got, which is seawater. Now, seawater is about half mold in sodium and in chloride, has of course a lot of other ions that would completely gunk up a commercial-grade system. The question is, how can you build resiliency so you can use this type of feedstock that can work with seawater and work with tap water directly? And that avoids a lot of the capex of the plant. And so there it's not just about the catalyst, but that's hugely important. It's also about controlling ion transport in the system. And so without diving too deep into the details, our research crew here takes periodic trips to Half Moon Bay. It's about a 25-minute drive from Stanford, a very beautiful spot where you can pick up some fresh Pacific Ocean seawater, bring it into the lab, purify it, and we've been able to show that we can now run these electrolyzers for 100 hours continuously. And not only do they operate, but they don't produce any chlorine, any bleach, or other free chlorine compounds, which is really important because if you end up making those, these are obviously very toxic compounds, very corrosive compounds, which ultimately equals more capex or operational costs of having to clean that up. So there's more opportunity that in dealing with impure feedstocks that we're focusing on. Another question is, how do you couple the sunlight? And there's lots of different ways to do this, and it ends up being very much a system-level approach. So I want to show some work from St. Lindsay and Jesse and GM. GM is a former PhD student who works with Jim Harris, who's a professor of electrical engineering at Stanford and works in semiconductors and photovoltaics. And the question here is, if you want to couple electrolysis to PVs, how would you do it? Let me just take a moment to just reflect on where the PV industry is. The most efficient solar cells we human beings have developed are about 46%. That's the record these days, which I think is absolutely outstanding. I mean, think about it. Sunlight coming in, you convert 46% of that incoming energy in photons into usable electricity. That's absolutely remarkable. But interestingly, that really high performance 46% PV might not be a great one to drive an electrolyzer. Because photovoltaics, the output power is measured by voltage and current, and you can trade those two things off to maximize power. But at the end of the day, if you're making hydrogen, what counts isn't the voltage. What counts is how much hydrogen molecules, what's the rate of hydrogen production. And so this really is a system-level design. So we designed in concert with Jim Harris and Gian and others, a photovoltaic that was 39% efficient, not too shabby. And the point is, the current voltage curve was such that we could not only get one electrolyzer in there, but we could sneak in two. And this doubles the amount of hydrogen production you can get through the system. We designed these electrolyzers to really be maximized in terms of efficiency more than anything else, and ultimately we have an average solar hydrogen efficiency of about 30%. So now we're not converting that sunlight into electricity, but into a storable medium, which is hydrogen, at 30%, which is pretty good. This is ridiculously expensive though. These electrolyzers are chock full of precious metals, and this triple junction UV is not cheap in its own right. So there's lots of opportunity to innovate in this space, but just really to show what we can do. In fact, this is not only the highest efficiency we know for any solar-driven electrolysis technology. It's the highest efficiency we know for any solar to hydrogen technology out there. Now, another approach here is if you want to cheapen the cost, you can try to integrate the semiconductor and the catalyst into one device. And so this is in partnership with the National Renewable Energy Lab, where that's exactly what we do. We take some of these multi-junction 3,5 materials, PVs, very high performance PVs, layer catalysts such as aluminum sulfide we talked about earlier, directly on the surface, stick this thing in acid, shine light on it under true on-sun conditions, and there's a solar radiation research lab at Emmett, where you can put this thing on the rooftop and at a cold day in January, actually be making hydrogen. So this system showed, for instance, 12.8 efficiency on direct solar hydrogen production under these circumstances. Real world conditions. Much that we need to dive into here to understand how to make these things durable enough, not to last just one day, which is about how long this one lasted, but to actually last a decade or more. Now, with that as a foundation, my hope is that you've seen a lot of opportunities to develop catalysts, develop chemical processes for hydrogen, which is one of the most important molecules that we use on Earth, and to simply leverage that and say a few words about carbon-based chemistry and chemistry. And so with carbon-based chemistry and CO2 electrolysis, there's a big issue that we have to face with hydrogen, and that is selectivity. Hydrogen catalysts typically are 100% selective or close to it to making hydrogen. If you throw CO2 in the catalyst, what's it going to do? Some catalysts don't even care that the CO2 is around, and they'll just make hydrogen anyway. And some of them will put the electrons into CO2 to make C1 products, could be formate or carbon monoxide or formaldehyde or methanol or methane. Sometimes you can do CC coupling. You can make hydrocarbons, you can make different types of oxygenates, aldehydes, ketones, all kinds of different systems. So how do you steer selectivity in this world? Not so easy. And so I want to point out a large number of scholars in our team that have worked on this over the years, really starting with Kendra, Natasha, David, Toru, Jeremy. Back in the day, and Natasha has launched a company since called Twirl that is now commercializing this technology, and the community has really moved far and fast in this space. Now with hydrogen, I talked a little bit about the technical economics there. In CO2, they look good as well. They look promising, we just need to innovate on the technology to get there. And so this is just some high-level technical modeling for, say, for making carbon monoxide or ethylene. And the point is that electricity is cheap enough, and if your energy conversion is high enough, assuming a lot of other factors, you can be in a profitable region where you can actually make these molecules cost-effectively. But one of the challenges, as I pointed out, with selectivity, and this is some of our original work in the space, again, harkening back to the days of Kendra, Natasha, and David in the lab, where if you just take carbon dioxide, infuse it in water, basically Perrier, synthetic, you can think of it that way, stick a copper electrode, standard temperature and pressure, and give it some voltage. These are the types of products that you can make. And it's a wonderful list of products. Some of these are produced at the megaton scale or tens of megaton scale or higher. So they're very important, but the problem is, as you can see, as you track the voltage and current of these different products, the challenge is that they're all kind of coming out at the same time. So it's a big separation from measurement. And what you really want to be able to do is just make the one product you want and not the ones that you don't want. So there's a lot to understand about this mechanism. And here's just a diagram that'll probably hurt your eyes and strain your eyes just to stare at it. It's really complicated. Taking carbon dioxide and putting electrons into it, you start reducing it, and you go down this pathway, you might use some CC coupling and make some C2 products here. There's a whole other section of this diagram that's not even shown for C3s, which we know we can make as well. And so there's a lot of open questions in this space. I'm going to note some of them on the slide here. One of the few things that the community seems to agree on is that formate is a dead-end catalytic, meaning that's your terminal product, you're good to go. But formate, really, we don't expect it to go much further along this diagram. The key species is carbon monoxide. So if you make carbon monoxide, then you can go further to make these other products. There's questions versus how do we, for instance, how do we separate hydrogen? If you're making a hydrogen electrolyzer, Great, but that's not what this is about. We want to convert CO2 into carbon-based products. And if you're converting CO2 into carbon-based products, how do you favor, say, multi-carbon products over C1s? How do you favor, say, oxygenates versus hydrocarbons? How do you selectively produce a single desired multi-carbon oxygenate? There's all kinds of questions here. Now, for those of you who work in thermal heterogeneous catalysis, this is not too different from the processes that we know and love today. Methanation, methanol production, Fischer-Tropsch synthesis, higher alcohol synthesis. And so there's a lot that we need to understand about pathways in those more, I would say, longer standing areas of catalysis. And the question is, how can we take that knowledge and put it into this one in the electrocatalytic world and vice versa? And so for that, I'm going to take a little aside here and ask this broader question of how do you bridge thermal heterogeneous catalysis and electric catalysis? And this reaction is as good a one as any. We know we can electrochemically convert CO2 into CO electrochemically, and of course there's water gas with. We can do the same thermochemically. And so there's a lot that we can understand by reading literature and understanding catalysts in these cases and doing computations and simulations as well. But from an experimental point of view, what I have long wanted to do is make a catalyst in a single batch, a single powder. I can take some of it, put it in a packed reactor, and some of it put in an electrochemical cell. And then you have an apples-to-apples comparison on the exact same catalyst that doesn't transform, and that's a big key. That the surface remains what you expect it to be, and you can drive these two reactions. And so that's something that we've long wanted to do, and we finally found a system that was capable of doing that. And that is these nickel nitrogen-built carbon catalysts. So there's a PhD student, recent graduate, David Koshi, worked together with Cindy Megan, who's current PhD student at Stanford University, supervised by Stacy Beck. David was co-supervised with me and Jen Kyle, who was a polymer chemist. And so David has been synthesizing these types of catalysts, basically taking nickel precursors, blending them in with polyacrylonitrile, pyrolyzing them to form motifs as you see here. Not too different from a nickel phthalocyanine molecular catalyst that people have shown that can do CO2 to CO electrochemically. We've shown that this catalyst can do CO2 to CO as a solid state catalyst. The motif is very similar to the molecular analog. And through this work, we showed that this is also capable of doing reverse water gas shift chemistry, as you can see here. So again, synthesizing a powder catalyst, taking half of it, putting in a catalytic reactor, the other half in an electrochemical reactor, and we can, in both cases, be very effective at making carbon monoxide or CO2. So there's a lot that we can dive into this now that we've got a catalyst that can operate in both scenarios. So we did the kinetics. We did the kinetics electrochemically. We did the kinetics thermochemically. Interestingly, and not surprisingly, the reaction rate equations are both exponentials. Surprise to probably no limit here. Though the electrochemical one has voltage as part of the exponential, which clearly, of course, that's not going to be in the thermochemical case. And one of the things when you take a look at, again, normalizing the surface sites and specific sites, going back to Paul Emmett himself, if you take the reaction rate of how much CO is being produced per nickel site per second, you can notice that the electrochemical case is actually orders of magnitude faster, interestingly, versus the thermal heterogeneous analysis. Now, of course, this is a manifestation, or I should say it's a manifestation. It's not so obvious as that turnover frequency is so much greater here than it is here when you do the measurement, because the packed bed is a three-dimensional reactor. You're packing that thing with powder, and you're making a lot of product. Whereas the electrochemical case is really not having any surface sites, it's really a two-dimensional electrode. And so we try to understand what's going on here from the turnover frequency. And so what David did is he basically converted the thermochemical equations and the electrochemical equations into a single non-dimensional equation that tries to capture the driving forces at play. And then when we plot the production rate of CO as a function of this dimensionless driving force, what you find is that the electrochemical, and which is up here, and the thermochemical almost directly line up. And so really this is a manifestation of the electrochemical driving force. When you start tipping your voltage to negative 0.4, negative 0.5, negative 0.6 volts, that's actually a huge amount of thermodynamic driving force you're giving the reaction, which is why the reaction rate is so much intrinsically faster in the electrochemical case versus the thermochemical case. But that's just the tip of the iceberg of what we're understanding here. The activation energy in the electrochemical case actually is substantially lower than that in the thermochemical case. And so why is that? And that's a complex question to answer. But to us, this is really screaming solvation effects. That's one of the key differences in the electrochemical reactor. We have a true solid liquid interface with ions, anions, cations, cozying up that interface can play a huge role in the kinetics of those electron transfer reactions, and it could very well be that that's the basis for a difference in activation energy here versus here. So this is really a way of trying to bridge different disciplines in catalysis. Again, nickel phthalocyanine is an molecular analog. The electrochemical solid state analog is this nickel nitrogen carbon, which is also good for reverse water gas shift, as I'll show you where I'm going to go. So this is really where a lot of, I think a lot of interesting science resides. How can we take what we've learned in these two communities, find that sweet spot, and kind of universalize understanding in chemical transformations. Now with CO, if we can make CO sustainably, what can we do with it? And so there's a lot that we can do with it. And so I want to point out some work from Lay, from Steph, and from Chris on what we can do with carbon monoxide reduction as opposed to carbon dioxide reduction. And so on this voltage scale, you can see this is the voltage versus reversible hydrogen electrode again. It turns out the equilibrium for the CO2 reactions is pretty close to zero. It's true for CO reactions as well. And we had this hypothesis that, of course, as you tilt the voltage more negative, you're going to get a higher reaction rate for CO reduction. And what this plot is showing in blue is you go to higher roughness factors, higher surface area electrodes, then you should be able to get a higher geometric current density, more production. But this might come at a cost of selectivity, because if you tilt the voltage more negative, you're tilting the thermodynamic driving force towards potentially more reduced product. And that's what we're showing here in green, is that if you want to make oxygenated compounds, if you go too far negative, yes, you have a higher reaction rate, but then you sacrifice your oxygenates and you end up making hydrocarbons. And we think oxygenates might be earlier kind of market adoption type of molecule. So we want to operate closer to equilibrium. It's more efficient and should produce a higher selectivity oxygenate. So based on this hypothesis, we wanted high surface area systems for CO reduction, and they went about synthesizing, working off of literature preps. This is very high surface area electrodes that came from the supercapacitor world. And without diving too deep into the details, we saw a tremendous change in selectivity. With the work of Kendra, Natasha, and David from back in the day, we saw 16 different molecular products when we threw CO2 with copper. Now with these copper nanoflowers, very high surface area, operating in alkaline environments, using CO as a reagent, operating much closer to equilibrium. You can see only 3 products really, which is ethanol, gas, acetic acid, and tallow, instead of 16 products, and all of these, of course, are multi-carbon oxygenates. If you crank the electrode more negative voltage, you speed up the reaction rate, but then you start making more reduced products, and you start losing that selectivity. We can take this a step further and say, how can we decorate that copper surface to even engender more selectivity towards the desired product? And so we started looking into silver-based systems. Theory was very helpful in pointing out why silver decorating a copper surface with silver could help change those pathways. And indeed, we were able to show that now at this point, whether you use these nanoflower, high surface area morphologies, or even a flat copper silver surface, we have tremendous selectivity towards acetaldehyde, which is just, of course, one specific multi-carbon oxygenated compound. And so if we go back to this pathway, you can see that going from CO down to acetaldehyde, normally it's really tough to think about how to do this with such a complex reaction network. But there are strategies, and you can't have to throw everything in the kitchen sink at it. It could be electric surface area, it could be electrolyte composition, it could be voltage operating conditions. There's so many different surface declarations. The point is there are pathways to do it. But then, of course, the big question is, how do you get to the CO in the first place? So we talked about some of David Koch's catalysts. There are other catalysts, conditional alloys, for instance, Farrell and Dave Wakely worked on in our lab. I'm not going to dive into the catalytic details here, but just to show you that we leverage some of our expertise in building membrane electrode assemblies with water electrolysis and pointed them towards CO2 electrolysis, and we're feeding in CO2 and making carbon monoxide. Here's the performance over a 40-hour time span, basically 100% of the electrons are going into CO. And then the question is, what do you do with this? So now, if you can make a reactor, a membrane electrode assembly, you feed in CO2 and make CO, let's say 25% single pass conversion. Is that feed, or is that effluent a potential feedstock into other processes? And the answer, I think, is yes. And so just to really take us out of our comfort zone, we work with the microbiology team, Alfred Sporman and his postdoc, Frauke Krake, who worked together with Sarah. And Frauke is a microbiologist who worked on a number of different species, including Clostridium ovoathanaginum, which is a microbe that's capable of uptaking CO and making acetate and ethanol. Of course, biology has some very selective processes that we could potentially leverage. And so the question is, was this effluent from our reactor biocompatible? And the answer is yes. So we fed it in, and almost 100% of the CO that came out of the reactor that went into the fermenter turned into acidic ethanol, exactly as you expected, based on the metabolic information we had on this particular microbe. When we fed in control of hydrogen and CO2, it did almost nothing. So this is just a way of saying that cascade catalysis tandem schemes have a lot of potential. We shouldn't think about electron-driven chemistries or temperature pressure-driven chemistries. The question is, how can we combine different forms of catalytic transformations to work in concert? Now, I'll wrap up in about 3 minutes. I just want to say a quick few words about ammonia production, which is the hardest reaction of the bunch, and N2 to NH3, again, working with a great team of scholars from a center that is led by my former postdoc advisor, in Korkendorf. And it's amazing to have those processes at feeding the globe, after fixing nitrogen in your body, touch the catalyst. It's an amazing process, but unfortunately, what comes out of plant gate and what ends up in the crop are two different things. There's a lot of waste of that ammonia, and that's really more to do with the distribution system than anything. The process here is beautiful, the distribution system is not. So very little ends up in the crop, a lot of it ends up as an environmental problem. And what we'd love to have instead is a more on-the-fly system that you can put into your agricultural field, takes in sunlight, directly converts N2 from the atmosphere into ammonia, and goes into the crop. And the long and the short of it is, in principle, that's possible. The reality is that hydrogen evolution is strongly favored versus ammonia production. And so you're going to just make lots of hydrogen instead, which again, in this application is not what you're looking for. So that's really got us in the community thinking a lot about non-aqueous chemistries. That's what I'm going to encourage those of you who are interested in this space to go into. And I'm just going to show you one of many different manifestations of this. This is work from Uschi, Josh, and Jay, who subsequently founded a company called Nitricity that is aimed at decentralized ammonia production. And the idea here is you can use renewable electricity to take a lithium hydroxide in a molten salt, electroplate the lithium, expose it to N2 to make a lithium nitride, dump it in water, you hydrolyze it to make your lithium hydroxide again, along with your output of ammonia. Take that lithium hydroxide and cycle it back over and over and over again. And the key with this is that where your chemical transformations are happening here is distance from where the water is. If you're dealing with 55 ml of water, really tough. So much proton in there, and then making lots of hydrogen instead. And so if you take a chemical process like this one, and you want to make, say, 100 kilos of ammonia per hectare per year, which is what a typical agricultural field would need, this process that I just showed you only needs about 5 square meters of solar cells, even though it's 4 canister. So just a way to show you that it is technologically feasible to decentralize the ammonia production process. The question is, how can we make that better? How can we use our knowledge of catalysis to do so? Last point I'll make here is that for those of you who are interested in ammonia, it's very challenging to do the reaction at all, and so measuring minute quantities is oftentimes a success. We just have to make sure that we have rigorous protocols to know that the ammonia that we're detecting is actually produced from the nitrogen that we feed into the system, and not just from ambient sources. So I just want to point out a few different papers that we've been working on. It turns out a lot of our contributions in this space are really developing rigorous methods and protocols to even do the chemistry, to know what you're seeing is something that you can trust. So with that, I'm going to wrap up. I just want to say, through catalyst design and process development, there are a lot of promising pathways to the sustainable production of fuels and chemicals. Showed you a few examples of hydrogen, carbon-based chemistry, and nitrogen reduction to ammonia. And I want to thank my research team and my colleagues, the Office of Science, Basic Energy Sciences, which funds the Suncat Center, along with a number of other federal agencies and industrial partners. I thank you all for your attention, and I look forward to seeing you throughout the week and talking some shop. Thank you all.
Thank you very much, Professor Jaramillo. Thank you very much, Professor Bell, for introducing him. Just a couple of announcements before you go. And one thing that I'd like to make a connection to, we have the community back together for the first time in a couple of years. And, slide, please. And we would like to try something. And I can't think of a better connection to today's Emmett winner in terms of what we are looking to do. Thursday, there is a panel session, and it's termed The Future of Catalysis for Sustainable Manufacturing. This is a program. You could see the abstract and kind of get an idea of what's going to be discussed. We have 3 panelists to kind of give us some thoughts on the future of what they see. Dr. Niels Barkley from BASF, Dr. Nagora Savio from ExxonMobil, and Dr. Vivian Schwartz from the DOE. The moderators will be Stu Soled, the honorary chair, as well as Deirdre Dunn, who is the executive publisher of Elsevier. And the idea behind this is to engage the community. And with the idea that now that we're back together, and we know that while we could always virtually look at one another and just chat, this is an opportunity to discuss. And with some of the ideas and work that we've seen with Professor Jaramillo, really I think should inspire us. There are also other sessions going on, kind of on these themes. And what we're going to do is work this 2 ways. One is we're going to have a Slido app, and that's on the right-hand side there. You could join at that number. You don't need to take the QR code from here, but it'll be shown around. It will be sent out to you by Mackenzie, who has been excellent in the communications area on our team. And with the app, what you can do is input questions in terms of what you think should be asked to the panel. And then everyone will get to see those questions, and then you can promote them if you like. You can add your own question, or see a question that you like and promote it. And when we come to the session on Thursday, we will have a number of these queued up, those that have gotten the most promotion or the most interesting, and those will be brought to the panel. But in addition, on Thursday, at the plenary session, so this time on Thursday here, we'll also have live questions as well. So the idea will be take some questions that have kind of been aggregated, crowdsourced, if you will, from our group here that is now together discussing, thinking, and talking about what is the future of catalysis for us, and what direction should we be going, what challenges are we going to face, and what do we need to do. And then, of course, we'll be here to have those live questions. So please participate as you can. It will be closed on Wednesday afternoon, because of course we'll have to do some work to put those questions together and get them to the panelists and get them to the moderators. So from now until Wednesday afternoon, you have the ability to put questions in, look at those that have been asked and promote them, and then of course please come to the session to have the discussion and generate some live questions that can follow up. Second, today opens up the exhibits. And again, being back live, the exhibitors who make some of the technologies that can help us move in the future are there for us to see, talk to, what they're making, what they're thinking, and so on. So please visit the exhibitors. The coffee will be in the exhibit hall. There'll also be the breakout sessions as well, but the coffee to the exhibit will be happening today as it's opened up. And finally, for those who have not collected their Yankee tickets, it's going to be a great game. It's the Yankees, the most winningest team in the world here in New York City. That's why you're here. That's why you're here. In addition to great signs and so on. So again, do the slide up, then go to the Yankee game. But if those who haven't collected their tickets, please do so. And if you did not get a QR code for your tickets already, that will be issued to you shortly. Please look at local arrangements if you need any help with that at the registration desk. So with that, I would like, again, to thank you all for attending. I would like to, again, congratulate Professor Jaramillo for an excellent talk and a well-deserved award. And have a great session. Thank you very much.